Yeah, in fact, my own experience, both when I was a student going to university for the first time to study mathematics and then teaching this kind of material over many years, is it's often the brightest students at high school that have the most difficulty when they get to university, and many of them actually drop mathematics at the end of the first year, if not the first semester. And it's sometimes the history major, or the intended history major, who somehow walks into the wrong classroom almost at the beginning and gets hooked within the first 2 or 3 weeks and ends up becoming a math major and then a math PhD. It really can be a crossover for many people, because university mathematics is so very different from high school mathematics. I don't know if you have remembered having a similar experience, or?
Yeah, I mean, as a student who went to St. John's, we do the Great Books program and we actually start with Euclid, and we have, I mean, a huge range of different types of students there. But many students come in with, I mean, for example, I took AP Calculus as a junior in high school, and it was a very different way of thinking about mathematics for me. When I went back and we started doing Euclid, I was like, oh, geometry, I took this a long time ago, but it's actually, I mean, it's it's actually quite challenging to think through the way that Euclid is doing his proofs, and it's a whole different way of thinking about math. You know, debating about definitions, trying to understand the meaning of proofs. It's very different than what I had learned and had become very good at as a calculus student.
Yeah. I mean, it's worth noting that students go through school system, but almost everything they learn up to middle school mathematics dates back from the 9th century. The rest of it, when they go to high school level, latest is 17th century. So for the last 300 years, mathematics has been developing at much greater speeds of development than previously. Most mathematics that we know actually was developed in my lifetime, and I'm not quite that old yet. When we think how much the world has changed in the last 10 or 5 years, it's kind of salutary to realise that we teach kids in the high school, through to the high school, with mathematics that hasn't changed for the last 300 years. And that's part of the reason why the kind of material we're talking about here is such an essential first step for students. They've got to make that transition to mathematics of the last 300 years from mathematics of the previous couple of millennia.
What you were saying, Keith, made me think too about, I mean, it's an interesting phenomenon. I think as part of this kind of historical way that we teach math, we've also siphoned it off and kind of siloed it as this entirely separate discipline that is, I mean, I think we often see it as, we portray it as foundational for other courses or for other types of thinking. Like science is essentially applied mathematics. In some sense that's still true, but it's not true in the way that I think we generally tend to teach it as being true. We teach it as like, you learn how to do equations in math class, and then you use those equations in science class. In reality, it's much more, you learn how to think logically and how to construct arguments and how to understand what proof is and what implication is, and these kinds of really important concepts. And those are broadly applicable, not just in science, but in literature and history and education. And those kinds of things are foundational, and they're an important part of mathematics, but it's not just the equation side of mathematics. It's that thinking side of mathematics that's the foundation for a lot of other disciplines.
Yeah. No, I often point out to students and to their parents, in many cases, that when I grew up, it was actually very important to be able to learn how to solve equations. Now we have software systems that solve almost any equation you need. The important skill now is how to take a real-world problem, or a problem from science or within mathematics, and formulate that equation in the first place. Once you've formulated it, you can enter it in a spreadsheet or and solve it. But formulating the equation, modelling a real-world phenomenon, that's a hugely important skill today. And it's one of the things that can only be learned through a lot of pain, actually, the kind of pain that we're about to put people through in this course. Because going from procedural ability that you learn in high school to being able to just think out of the box about a new problem, that's a really hard skill to develop. On the other hand, once you've got it, the world is at your feet.
In many ways, I've learned that this type of course is the bridge then between K-12 school math and the real math that mathematicians do in the world. Does that sound accurate?
Oh yeah, what I see in the high schools is not at all what I do for a living, and it's not the fault of either group, although I think that it would be nice if the high schools had managed to get at least into the last 300 years rather than be stuck, although they stop at calculus, which is 17th century, and then an awful lot happened after calculus. In fact, mathematics had to change dramatically in the 19th century when mathematicians, what happened in mathematics was actually similar to what happened in physics. In physics, we had the discovery of relativity and quantum theory, neither of which could be understood intuitively. It could only be understood through the mathematics. The same thing happened within mathematics. We had to learn to trust the mathematics, not our intuitions. And that involved a new approach to mathematics.
Yeah, and I actually think that's a really strong analogy. I've actually recently been reading Gödel Escher Bach.
Great book.
It's a great book, and he talks extensively about Gödel and Gödel's proof, and the idea that there is no such thing as a system which is entirely complete. And he goes about showing how this is the case with various self-referential things. But all of that, it ends up being a very counterintuitive result in many ways. And I think that's what you're saying, is that it's, there's this counterintuitive nature of modern mathematics kind of since Gödel and since that time period where, we want to feel like, well, of course you can have logically complete systems. Of course you can you can have this perfect understanding of the world in some ways. But actually, results in physics, in chemistry, and mathematics have kind of shown that it's not that there's an essential relativism of the world, but it's more that there's and that anything goes. But it's more that there's a lot of complexity there, and there's a lot of, once you start putting self-reference into systems and you start thinking about recursive systems, you get these really complex and really interesting worlds, and that leads a lot into computer science as well.
And into our modern financial system, which is as recursive as it gets, which is why we have these huge fluctuations in milliseconds. Certainly, I think, my view is that the MOOC has probably come along at exactly the right time, because, for several decades we needed a few thousand people who could think this way. Many of them moved to California and Silicon Valley, as I did, because that was one of the foci of this kind of research. But now it's reached a stage where the whole world needs that kind of expertise. And so if we can take this technology, which was developed here in Silicon Valley largely, and spread it out to the rest of the world, then they can start to do the same kind of things that everyone does need to do now, because the skill sets that are necessary have changed.
In fact, in my area of learning analytics, which is deeply related to kind of data science and a lot of kind of those modern big data issues, there's a projected shortcoming in big data and data analytics and data science of hundreds of thousands of people who are specialists in that area, and millions of people who are at the management level who are able to understand those kinds of mathematics, essentially at the level that they can actually have a communication with specialists and make decisions based on it. So there's a huge need for people who have this kind of mathematical thinking, which is the fundamental groundwork on which data science is built, is this kind of thinking. So there's a huge shortage of people in that area. So a lot of opportunity for anybody who is going to study this stuff.
Absolutely.